In this chapter, we're going to deal with energy, which we've already spent quite a bit of time in the course talking about. Energy we defined earlier as not some kind of an invisible fluid that's inside of something, but an ability that something has. Specifically, it's an ability to do work. We've already talked about what work was. Work is pushing an object, I should say, not just pushing, but moving an object against an opposing force. So if I'm lifting a weight, the opposing force is gravity, and I'm moving it against that opposing force, so I am doing some work. If I have some energy, I am able to do work. If I did not have energy, I wouldn't be able to do that. Work is, since it's moving an object against an opposing force, you take the size of that force and you multiply it by the distance that you move it through. And that is the amount of work that you did. Now, we've seen that the SI units for force were the Newton, which is a kilogram meter per second squared. Capital N is an abbreviation for that clump of units. And then if you multiply that by distance, the SI base unit for distance is meters. So you put these together, you get Newton meters, or you could write it out as kilogram meters squared per second squared, or you should know the other name for this clump of units. It's the joule. So joules, which has an abbreviation J, are the unit of energy. And the units of work are the same as the units of energy then. Work is an orderly transfer of energy. So imagine you've got a bicycle pump and you're compressing the air in the bicycle pump. It gets warm. The heat that comes out of there is kind of due to the random kinetic energy of the molecules. The molecules are just moving in every direction. So that heat that comes out is disorderly, but the work that goes in is orderly. Here's another example of what I mean by orderly. Suppose you've got the gas in the bicycle pump and you push the piston in. Now the gas molecules are going to be pummeling against the surface of the piston as it moves in and resisting it. So that's the opposing force the gas pressure provides it. The orderly transfer of energy is that the kinetic energy of the piston here is going to get transferred into the gas. And it's orderly because all of the little atoms that are in the piston are all moving forward in lockstep. They are all moving together forward and transferring some of their energy to this. Now, to really understand what's going on here, we have to look at the kinds of energy that we've got. There are really two kinds, and we've already talked about this too. There's kinetic energy, and there's potential energy. Kinetic energy is energy of motion. Now, even something that looks like it's stationary, like this pen, has some kinetic energy because the molecules inside of it are moving around. When you talk about the kinetic energy of molecules inside of an object that isn't moving overall, you're talking about one component of internal energy. Potential energy is energy of position. For example, if I've got a mountain here and there's a boulder teetering on the top, it's got some potential energy because it can roll down the hill spontaneously. If you tap it a little bit, it'll start moving down. That potential energy can get changed into kinetic energy. So these two type of energies can be turned into each other. As the boulder is rolling down the hill, it has a lot of kinetic energy. And it will eventually stop down at the bottom. It'll hit the bottom. And when it hits the bottom, maybe it'll smack into the bottom and make a sound. Some of the energy is being dissipated as sound. So energy can be converted into different forms. So imagine that you've got a pendulum. And you can swing the pendulum. In the next minute, it swings up maybe that high, and then it stops there and it turns around. Now, when the pendulum is up at the top of the swing, it's got potential energy. Which we can write in terms of the height that it is above the lowest point of the swing. This is the mass of the object. This is the acceleration due to gravity. We used this a little bit in the last chapter. And this is the height above the bottom of the swing. If you look at the units and try this yourself, you'll see that they come out to be the same units that we have up here, which are energy units. Now when you're at the bottom of the swing, all of the kinetic energy is energy of motion. All the energy is kinetic energy, which is energy of motion. And you can calculate that too from the speed that this thing has. It's 1/2 mv squared. We've used that equation a little bit before too. So as a pendulum swings back and forth, it is converting potential energy and kinetic energy into each other. But the total energy is constant. If you added the total energy, the kinetic energy plus the potential energy at any given point as the pendulum is swinging, you get the same number. This is a way of saying energy is conserved. That is, it doesn't go away. It's not created out of nothing. Only transferred. You can move energy, this ability to do work, from one place to another, from one object to another. So if you wind a watch, you're putting some of your energy into potential energy in the spring, which then can be converted into kinetic energy, which would be the motion of the hands on the watch, if you had an old style watch that you could wind up. energy, the statement that energy is conserved is another way of saying the first law of thermodynamics, which is what we'll talk about in the next video.